We are recording.
Thank you, Deirdre. All right, good morning, good afternoon, or good evening, everybody, depending on where you are located. It is my pleasure to welcome you to this final day of our Cardiovascular Health Tech Conference, sponsored by the IEEE Engineering and Medicine and Biology Technical Committee on Cardiopulmonary Systems and Physiology-Based Engineering. My name is Thomas Held, and I'm the past chair of this technical committee and associate professor of electrical and biomedical engineering at MIT. The conference is also co-sponsored by the IEEE Engineering and Medicine Technical Committee on Wearable Biomedical Sensors and Systems, as well as the IEEE Signal Processing Society Technical Committee on Applied Signal Processing Systems. Today's 2-hour session will cover the future of cardiovascular health tech as we see it today. The session is intended to be interactive with the audience, so please do submit questions and comments via the Zoom Q&A option. Your questions can be directed to the speaker or the session chairs. The session will also be recorded and available as a private YouTube link, which will be emailed to all registrants soon upon completion of the conference. So with that, it's my great pleasure to introduce today's co-session chairs, Dr. Nanshu Liu and Dr. Roozbeh Jafari. Dr. Liu is a Frank and K. Rees Professor at the University of Texas at Austin. She received her BEng with honors from Tsinghua University in Beijing, a PhD from Harvard University, and then conducted a Beckman postdoctoral fellowship at the University of Illinois at Urbana-Champaign. Her research concerns the mechanics, materials, manufacture, and human or robot integration of soft electronics. She is a Clavariate, highly cited researcher and a fellow of the American Society of Mechanical Engineers. She is on the board of directors of the Society of Engineering Science. She is currently an associate editor of Nanoletters and Journal of Applied Mechanics. She's also been named 35 Innovators Under 35 by MIT Technology Review. Dr. Roozbeh Jafari is the Tim and Amy Leach Professor of Biomedical Engineering, Computer Science and Engineering, Electrical and Computer Engineering at Texas A&M University. He received his PhD in Computer Science from UCLA and completed a postdoctoral fellowship at UC Berkeley. His research interests lie in the area of wearable computer designs and signal processing. He serves on the editorial board of many IEEE publications, including the Transactions of Biomedical Circuits and Systems, Sensor Journal, the Internet of Things Journal, and the Journal of Biomedical and Health Informatics, as well as Nature Digital Medicine and the ACM Transactions on Computing and Healthcare. He is currently chair of the IEEE Wearable Biomedical Sensors and Systems Technology Committee, as well as the IEEE Applied Signal Processing Technical Committee. So thank you, Dr. Liu and Dr. Jafari, for co-chairing the session. I'll turn it over to you now.
Thank you so much, Dr. Helt. It's a pleasure to be here. I am going to co-chair this meeting with Dr. Liu, and I have the great pleasure of introducing Dr. John Rogers. John obtained his BA and BS in chemistry and physics from UT Austin, his SM and PhD in physics and chemistry from MIT in 1995. He was a junior fellow at the Harvard University Society of Fellows. He joined Bell Lab as a member of technical staff in 1997, and he served as a director of this department from the end of 2000 to 2002. He spent 19 years at the University of Illinois, and most recently as Swan Lund Chair Professor and Director of Sites Material Research Lab. In fall of 2016, he joined Northwestern University as the Louis Simpson and Kimberly Query Professor of Material Science and Engineering, Biomedical Engineering and Medicine, with affiliate appointments in Mechanical Engineering, Electrical and Computer Engineering, and Chemistry, where he is also director of a recently endowed Query Simpson Institute for Bioelectronics. He has published more than 700 papers, is a co-inventor on more than 100 patents, and he has co-founded several successful technology companies. His research has been recognized by many awards, including MacArthur Fellowship, Lemelson MIT Prize, the Simpsonian Award for American Ingenuity in the Physical Sciences, and the MRS Medal, and most recently the Benjamin Franklin Medal from the Franklin Institute. He is a member of the National Academy of Engineering, the National Academy of Sciences, the National Academy of Medicine, the National Academy of Inventors, and the American Academy of Arts and Sciences. John, it's a pleasure to have you. You may take it away, please.
Great. Thank you very much, Ruzbeh, for that quite extensive introduction. Appreciate that. Thanks also to you and to Nanshu for inviting me to participate in this exciting discussion around next generation technologies for cardiovascular monitoring and therapy. And so I'll share with the group some of the work that we've done in this space over the last 10, 15 years or so in the next 25 minutes. I'll begin with a background, a little bit of overview on the technology foundations for our various devices, but really focus on system level implementations that address real medical needs in cardiac monitoring and cardiac care. Two specific platforms, the first of which is characterized by soft skin compatible mechanical properties, physical forms that we refer to as epidermal electronics. And I'll show you how those types of platforms can be used for wireless ICU grade monitoring of cardiopulmonary health. And then in the second part of the talk, I'll describe another class of technology that we've been interested in that is uniquely defined by its ability to dissolve in biofluids. So it's bioresorbable electronics as temporary implants, engineering forms of medicines in a sense. And I'll show you how those kinds of platforms can be used as alternatives to the sort of temporary pacemakers that are typically used with patients after a cardiac surgery. So my home appointment is in material science and engineering. I think that's kind of my core expertise. But as you'll see, we're interested in multidisciplinary research and sort of engineering at a system level, oriented around attempts to develop technologies that can improve the way we think about human health. And so I have deep engagements with the clinical community through appointments in our medical school and engagements with a broader clinical community here in Chicago. So over the last 15 years, we've been attempting to develop engineered systems, electronics, microfluidics, microelectromechanical systems, microsystems technologies in general that adopt physical forms that are compatible with soft tissues of the human body. And you can think about that maybe most clearly as interfaces to the brain. Electronics in, on, or around the brain could be important for understanding brain function, but also delivering therapies to address brain and mental disorders. But in the context of this presentation, I'll focus on those classes of devices as interfaced directly to the heart for cardiac electrotherapy and interfacing to the surface of the body, the skin as a point of contact, as a non-invasive way to measure cardiac health and to track that continuously. So I won't go through the details of the underlying technologies. This is something that we and others, including Nanshu, have been working on over the last, 10, 15 years. But the point is that there are collections of materials, hybrid, hard, soft material systems that can be configured into platforms that have soft, effective mechanical characteristics in non-planar configurations that allow chronic, stable interfaces to soft moving tissues of the human body. And it's really an exercise in mechanics design and circuit design to build these classes of devices that can provide, in many cases, clinical grade monitoring capabilities, but in a fashion that allows for continuous tracking, not only in confined hospital and laboratory settings, but into the home as well. And so we and others, have been working in this space for quite some time. And at this point, there's a broad portfolio of devices with those kinds of unique characteristics that can be mounted really anywhere across the body to address particular monitoring needs and to address unmet clinical needs in monitoring of health status. So the idea is wireless, continuous, and multimodal in terms of the measurement capabilities. And this is a platform that we've been interested in and have really directed toward patients that are in greatest need for that kind of capability. And we really started with full vital signs monitoring in the neonatal intensive care unit, with the idea that these patients could benefit most strongly from a wireless skin-like alternative, the kinds of wired-based monitoring systems that are used today, even in the most sophisticated level 4 NICU facilities like those that we have here in Chicago, other places in the US, and with cost structures that will allow their deployment not only into developed parts of the world, but also into lower and middle income countries. So this was kind of a vision of what we had hoped to do with this technology. And over the years, we've been able to put together all of the capabilities for realizing that vision. We and others as well at this point. And this is a pair of devices that recapitulates all of the vital signs monitoring that's done in the NICU today. It's 2 units, one that mounts on the chest that measures continuously ECG waveforms and core body temperature through a digital temperature sensor embedded in the device. These are wireless battery-free devices with that kind of skin-like form factor. So the chest unit allows you to measure ECG, from which you can determine heart rate variability, respiration rate, and as I mentioned before, a pretty good surrogate to core body temperature. The other device measures blood oxygenation, typically mounted on the foot or the hand. And these devices are time synchronized, so you can capture hemodynamic information as well. So they're fully FDA approved. They've been deployed on thousands of premature babies at this point. Again, not only here in the US, but we've also deployed into Africa, Zambia, Kenya, Ghana, India, Pakistan, and Mexico as well, in partnerships with the Gates Foundation and the Save the Children organization. And they're fully validated at a quantitative level to reproduce waveforms that are indistinguishable, in many cases better, lower noise levels than those associated with conventional wired-based systems. This is a 28-week delivery that was part of an initial study that we conducted at Lurie Children's Hospital. So the NICU, but also the PICU as well, slightly larger babies, but also benefiting very strongly from a wireless alternative to the wired systems that are used today. For many reasons, and one of them is sort of illustrated in this picture. It really facilitates the kind of parent-child engagements that are known to have a therapeutic benefit on the developmental processes of the babies at this stage of their lives. So you can see the chest unit, the PPG unit, photoplethysmography is being performed on the base of the foot. We're doing wireless power transfer to provide the ability for these devices to operate, and that same magnetic inductive link is serving as a data communication channel as well. So as I mentioned, this is transitioned out of the lab at this point, FDA approved platforms deployed in more than 20 countries, and moving forward in the context of an engineering-oriented startup company that we have here in the Chicagoland area. But let me just focus on the actual data streams that emerge from these devices. This is a slightly more sophisticated version of the platform that I described a couple of slides previous, reported in Nature Medicine in spring of 2020. So the chest unit is capturing ECG, but it's also capturing seismocardiograms as well. So these are heart sounds, time synchronized. And then that limb unit is doing photoplethysmography. So you have some multimodal data streams that are all related to cardiovascular health. So it's a high bandwidth accelerometer in the chest unit paired with the ECG recording capabilities. So you get heart sounds, electrical activity associated with cardiac cycles, and then you get pulsatile waveforms from the PPG unit, all time synchronized to within about a millisecond, so you can get pulse wave velocity as well. And you get respiratory cycles from motions of the chest wall cavity. So the most primitive cardiovascular parameters that can be obtained from those kinds of data streams are things like heart rate variability, blood oxygenation, and so on. But you can actually do quite a bit more. And we've been interested, and this is a topic that's been studied extensively, not just us, obviously, but understanding that the time relationship between the electrocardiograms, the seismocardiograms, and the photoplethysmography, and thinking about the pre-ejection period, the pulse transit time, by looking at relative timing associated with these various events. And these kinds of time delays have been analyzed in the past using semi-empirical models of the mechanics of pulsatile flow of fluids through elastomeric pipes, essentially. And there's quite an extensive literature in this area. We collaborated with Professor Yonggang Huang here at Northwestern to, I think, put together a much more rigorous mechanics model based on a more sound physics foundation that had been published previously to relate pressure, blood pressure, to measurable parameters that can be obtained from the various timing events associated with these three waveforms that are being captured in a time synchronized fashion. And this is the kind of empirical relationship that connects blood pressure to PWV, which is pulse wave velocity determined by these time delays. And so this represents a semi-empirical way to attempt to capture continuous blood pressure, which is sort of the holy grail of monitoring, currently very difficult with these infants, neonates, and pediatric patients because of the very small, fragile nature of the arteries. It's difficult to get an arterial line in, and a conventional blood pressure cuff doesn't work very well because repeated use of that kind of cuff can lead to bruising and damage to the soft, fragile tissues of these babies. So a non-invasive way to sort of track systolic, diastolic blood pressure would be extremely valuable in the PICU and the NICU. And so here's some initial results where we're tracking with patients in the PICU actually that already have an arterial line installed. And so that's the set of results that you're seeing here in the red part of this graph. This is bedmaster, it's the arterial line. And then shown in blue is a calibrated measurement of systolic blood pressure inferred from pulse arrival time as defined by the ECG, SCG, and PPG waveforms. And so this just illustrates that this can work. This semi-empirical approach can provide the ability to track changes in blood pressure if appropriately calibrated for these very sick patients in the PICU and the NICU. And this kind of thing has been reported in the past for adults. I think this is the first time in pediatric patients. But the challenge here is that the calibration needs to be done relatively frequently, especially with these classes of patients which are undergoing various pharmacological treatments that can change the vascular tone and thereby alter that calibration factor. So the maybe more ambitious way to think about how to use the raw data streams in this context is to apply neural networks directly to the raw data inputs. So we have the raw data streams, time synchronized ECG, SCG, PPG, and now we have the arterial line measurements as well. And so the question is, can you create a neural network that connects the measured time series data directly to the full pulse waveforms captured with an arterial line? The hypothesis being that you have enough information in the ECG, SCG, and PPG to allow for that connection. And that's just a hypothesis. It might not turn out to be the case. So I actually spent a lot of time on this, developing CNNs with LSTM architectures for this purpose. And this is sort of an illustration of how that kind of network can gradually learn measured changes in blood pressure from the raw data inputs. And this can work relatively well. So you can train a CNN to do this conversion from these raw data streams into blood pressure. And we've done quite a bit of validation of these measurements. Not perfect, but you can certainly capture trends. And this is an illustration of that. We're using Finepress in this case to track blood pressure in an adult patient in the ICU setting at Northwestern Memorial Hospital, systolic and diastolic blood pressure in this case. And you can see the reference measurements. And this is predicted from a neural network trained from data collected from a different patient. And so in certain instances, you can certainly capture the trends, not all of the fluctuations. And I think there's uncertainty in the Finepress measurement as well, but showing some promise for this kind of capability. And here's another example of that, where we have in these stars sort of cuff-based measurements of blood pressure. We're showing the semi-empirical measurements derived from the data, the pulse arrival time specifically, and then the CNN approach applied directly to the full time series raw data. And you can see there's a difference. I would argue that the neural network approach is tracking better to the blood pressure cuff measurements than this semi-empirical approach. But this is very much ongoing work and continues to be a focus area for us and I think many others in this community as well. Now, the hypothesis is that ECG, SCG, PPG provides all of the information that would be necessary to determine blood pressure. It's not clear that that's the case. And so in parallel with these sort of machine learning efforts within the group, we're also developing new hardware systems that can add additional data that might ultimately prove to be necessary for a reliable prediction of blood pressure. And here's an example of one of those types of devices. It's a multi-wavelength PPG unit. So instead of just measurements in the red and the IR, it does measurements at 16 different wavelengths. And the advantage of that is you can start to determine pulse wave velocity in the capillary beds in a direction normal to the surface of the skin. And that's important because most of the systemic vascular resistance occurs in the capillary beds. And so with this multi-wavelength approach, you can add another pulse wave velocity component to your analysis that we hope and anticipate will further improve the accuracy of these blood pressure estimations obtained by machine learning techniques. And so this is some additional new work for us in this space. So that's all I have to say about these skin interface devices for monitoring cardiovascular health. How about therapies that could be delivered to the cardiac system to address patient needs? And in that case, you think maybe about implantable devices. And in many cases, at least in the cardiac context, you think about pacemakers as permanent devices designed to last the life of the patient. But there are instances where that kind of pacing could be done in a more sophisticated way, as illustrated here, multi-lead extending across the entire myocardial surface. But you can also think about pacing in the context of temporary patient needs. And this was an opportunity that was brought to us as a result of understanding of technology developments that have been pursued in our group that have led to the ability to build high performance electronic systems that can dissolve away in the body over programmed timescales. And this has been an area of interest for us for a while. And a couple of years ago, we were approached by cardiac surgeons, and they proposed the use of that kind of bioresorbable technology for temporary pacing. And I didn't realize that this was a standard of care, but evidently, if you undergo a cardiac surgery, in many cases, the surgeon at the tail end of that surgery will place a pacemaker, typically a single lead pacing device in the endocardial epicardial surface, and they place it there to allow the heart to be paced during that critical recovery period following the surgery on an as-needed basis. So if the heart rate drops below a certain threshold level, they can engage that temporary pacemaker to pace the heart up to a more normal sort of healthy rhythm. And then ultimately, after the patient emerges from that critical risk period following the surgery, that pacemaker is no longer needed, and thus it's used in a temporary fashion. And the current classes of temporary pacemakers that are used for those purposes are not bioresorbable, so they require a surgical extraction procedure that can impose risk to the patient. And so the vision provided to us actually by cardiac surgeons who do these kinds of operations was to remove or eliminate that conventional temporary pacemaker and to replace it instead with a fully bioresorbable wireless device that can provide that same kind of function, tuned through appropriate material selections to survive and offer a stable operating period aligned with that recovery timeframe, but then ultimately simply dissolve and melt away without a trace inside the body, thereby eliminating the need to do that surgical extraction. So this makes sense if that surgical extraction process is costly or it exposes the patient to additional risk. And it turns out that there are significant risks associated with that removal. And the problem is that these pacing leads typically become encapsulated in fibrotic tissue during that recovery period. So when they need to be removed, they're simply pulled out of the body. It's a transcutaneous interface to an external power supply to provide the stimulating pulses for doing the pacing. You pull it out of the body, that fibrotic tissue rips, and in certain instances, the tearing of that fibrous tissue can lead to damage to the healthy underlying cardiac tissue, thereby creating internal bleeding that can be a very high risk factor for the patients. And in fact, just as an anecdote, Neil Armstrong passed away because of complications associated with the removal of his temporary pacemaker after a cardiac operation. That led to an internal bleed that ultimately led to his death. So this is a risk factor that's important and one that can be addressed, at least in principle, with a bioresorbable wireless electronic system. And I won't go through the details, but we've been able to put together a device that satisfies all of those requirements. So it's a pair of pacing leads that we construct out of a combination of tungsten and magnesium, both bioresorbable metals. Those are coupled to a pair of inductive coils that serve as a basis for harvesting wireless power from an external transmission coil. That harvested power comes in as an AC waveform that we rectify with a silicon nanomembrane diode, RF diode. Silicon itself is bioresorbable. And then we use polymers that are known to be biocompatible and bioresorbable as encapsulation layers and as substrates. So it turns out to be a thin device that you can just affix to the epicardial surface, and then you can wirelessly activate pacing on an as-needed basis. And so this is what it looks like. It's very thin, flexible, does not impose any significant mechanical constraint on natural cardiac cycles, but does have the ability to pace cardiac rhythms on an as-needed basis. So we've done testing in small animal models, rats and mice, medium-sized animals, rabbits, canine models, porcine models, and even human hearts from organ donors to show that you can capture cardiac rhythms even at a human scale with these devices, and they're fully bioresorbable. So as one additional technology that I'll describe, it's really sort of merging those skin interface devices that I began my presentation with these sort of transient bioresorbable implants. And one of the disadvantages of the resorbable pacemaker that I just described to you is that it does require separate monitoring systems for tracking the cardiac rhythm to determine if the patient is undergoing bradycardia, for example, and is in need of pacing. That's typically done with a wired-based system that tethers the patient to hospital recording apparatus. And then it also requires an external box of RF electronics for doing inductive power transfer to the pacemaker. And so you can embed all of that functionality into these skin interface patches that I was describing before that were designed to measure ECG, SCG, and PPG. So here we have a chest unit that's capturing ECG waveforms, but it also has an inductive coil that can wirelessly communicate to the implanted bioresorbable pacemaker so that the entire system can run autonomously in a closed loop manner without any wire-based tethers to constrain movements of the patients. And so this is what the electronics look like in that particular patch. So we still have the analog front end and the ability to do ECG recording, but we also now have a source of RF power and a matching circuit to resonantly couple RF energy from this device to the implanted pacemaker. And this is an example of closed loop operation of that kind of system deployed in a rat model. And so we have that chest unit sort of strapped to the outside surface of the rat. We have an implanted bioresorbable pacemaker. And in this case, we're artificially creating bradycardia. And what you see is that once the heart rate of this animal drops below a set threshold, the system in a closed loop autonomous manner begins pacing. So it will pace the heart back up to a normal rhythm. It will cease that pacing and then monitor ECG again. If it's still below the threshold, that heart rate, it will pace again. It will continue to bounce back and forth in that way until the heart rate naturally moves above that threshold, and at which point it will cease pacing entirely. And so this is a system, combines these two technologies, epidermal and bioresorbable electronics, in a single system for doing cardiac monitoring and electrotherapy in closed loop fashion. So I think I'm out of time. I just want to kind of summarize. These are two technology platforms that combine, I think, innovation in material science, but also electronic circuit design in platforms that have relevance to cardiovascular health, monitoring systems that interface with the skin, electrotherapy systems that implant temporarily into the body to establish an interface to the heart for temporary pacing. So with that, I'll go ahead and conclude by acknowledging senior collaborators who are involved in this work. We're a very collaborative group. We work with a number of folks with expertise in engineering science that complements our own, but it's really that interface to the clinical medical community that's so important to everything that we do. And I want to acknowledge the various folks within our medical school and other areas of the medical community who've contributed to this work. But the most important people are the students, the postdocs who actually do the work. I just talk about it. And so I always like to conclude my talk by acknowledging them for their great ideas and their persistence and hard work. And I'd like to thank you guys again for inviting me to participate, and I'll be happy to answer questions if there are any.
Thank you so much, John. This was a wonderful talk. So we have time for at least one question, and I am going to read this from the chat. In the context of wearable monitoring applications of your technology, I wonder how long these systems can stay attached to skin, considering that skin is live and evolving. And how do you evaluate this technology in terms of skin irritation and beyond that, user comfort and adaptability?
Yeah, it's a great question. The skin is a dynamic system. Skin cells are starting in the base layers. They're differentiating, migrating up to the surface where they ultimately die to form the stratum corneum layer, and then they exfoliate. So if a device is sitting on top of the skin, it's frustrating that exfoliation process. And that sort of cellular escalator and differentiation process has a timescale of about 2 weeks associated with it. So I think 2 weeks is very doable. A month begins to sort of push the outer limits of what's possible. It's not a materials limitation. It's just the fact that eventually you're sitting on a accumulated layer of dead cells that's not very mechanically stable as an interface to the underlying healthy skin. And so that's typically the way we think about it. I feel like, for us, there's a lot of emphasis in ICU care, and there are a number of things that are happening as part of the care of patients in that context that are going on in a 12 or 24-hour time cycle. And so there are plenty of opportunities within that type of time frame to remove a device, refresh the skin, and replace it. So for the premature babies in the NICU, it's once every 12 to 24 hours, the devices are being removed and then and replaced. So this idea of multi-week monitoring is not so important for those patients. In terms of comfort and adaptability, I think it's partly a function, quite frankly, not only of the engineering, but of the need, and I think where we've started are not healthy, normal patients where you're sort of just tracking overall health status, but people who are critically ill and absolutely require this kind of monitoring. And I think patient burden is sort of correlated to patient need in a sense. And so we have not had any challenges in getting patient consents or buy-in from the clinical community as a result of that very strong need for the use cases that we're exploring.
Thank you for that. Thomas, can I ask one more question? Okay. Thank you for your very inspiring work. Are there any sources of power, such as batteries or energy harvesting, that can avoid the need for RF wireless power?
Yeah, it's a good question. We like RF wireless because you can throw a fair amount of power, without exceeding, thresholds that would be dangerous. And it's hard to get, milliwatts of power from energy harvesting. We certainly thought a lot about that. There aren't very many, significant thermal gradients within the body, so thermoelectric approach is not that attractive. We looked at harvesting power from mechanical motions. You can do that. It tends to be intermittent. You can put piezoelectric harvesters on the heart, the diaphragm, and the lungs. We looked at that. Not a lot of power generated in that way. I think it's a great area for continued research. But our RF wireless does a lot for you. And again, in that ICU context, it's quite sufficient. It doesn't provide full ambulatory freedom, but for the babies, they're in the isolate, where they are, you can wire that up with an antenna. It's not a significant constraint. I will say, however, that for deployment into these resource constrained areas of the globe, there's no reliable source of wall plug power in many cases. And that was a driving consideration to move for those devices, for those parts of the world, to systems that include a very small lithium polymer rechargeable battery within the device to provide more reliability in the monitoring capabilities, really driven by that consideration. So that's another option, and we've done that as well. Other groups have also done great work in this area.
Thank you so much, Dr. Rogers. This was such a wonderful talk. We appreciate your time. So I'm going to pass the microphone to Dr. Nanshu Liu for the next introduction, please. Thank you.
Thanks, Ruth Bay Zhang, for the brilliant starting of our third day. And I have the pleasure to introduce our second speaker today, Professor Xuanhe Zhao. He is a professor of mechanical engineering at MIT. The mission of his lab is to advance science and technology between humans and machines for addressing grand social challenges in health and sustainability. A major focus of his lab is the study and development of soft materials and systems. Dr. Zhao is a Clarivate, aka Web of Science, highly cited researcher. He's the co-founder of multiple startup companies that translate technologies developed in his lab. He has over 10 patents that has been licensed by companies and contributed to FDA-approved and widely used medical devices. His lab's invention of the bioadhesive ultrasound imaging device was selected among the 2022 Time Best Inventions, and we are fortunate to hear that today. He has a numerous long list of awards and achievements, which I will not be able to cover one by one, but he has been the principal investigator of dozens of nationwide and global clinical research trials, and has published 300 peer-reviewed articles, and has now many students and postdocs working in academia and industry. So Xuanhe is also a very close friend and actually also a peer role model and a mentor of mine for decades. So Xuanhe, it's my great pleasure to have you talk to us today. The floor is yours.
Thank you so much, Nanshu, for the kind introduction. Also, thank Nanshu, Ruth, and Thomas for this kind invitation. This is a great session that you guys are putting together. I learned a lot from John's talk. I'll continue the momentum. I'll discuss a bioadhesive ultrasound, continuous simultaneous multi-organ imaging for cardiovascular health, Xuanhe Zhao from MIT. Conflict of interest, I co-founded Sana Hill, receive royalty from CRS. This is the mission of my lab, merging humans and machines. The opportunity we see over the last century, there are great advances in terms of biology, medicine, genetics around the human body. In parallel, we see great advance in terms of semiconductors, electronics, computers, internet, robotics, AI. However, there's a huge gap between humans and machines. And my lab, and I think many other labs, in the audience and in the panelists are working on really merging these two domains. My group adopted an interesting approach. We call it soft materials technology. The idea is we design soft materials with very similar mechanical and physiological properties as different organs of the human body. Use that soft material to form long-term, high-efficacy, even non-fibrotic interfaces with diverse organs of the human body. At the same time, we make this soft material to be very robust, to be part of the machine, so that we can embed sensors, actuators, computer chips, even robots into this soft material interface, and using this soft material interface to form this merging between humans and machines. Today, I'll discuss one example, wearable imaging. So especially its potential impact on cardiovascular health. I'll begin with stretchable electronics, what John just give a beautiful talk on. So this is a field pioneered by John and a few other researchers over the last few decades. Great accomplishment. So the key idea is make electronic devices to be thin, stretchable, conformal to the skin, so that they can deform together with the skin and even other organs of the human body. And these devices has been widely used for measuring ECG, EMG, EEG, heart rate, temperature, sweat, many other physiological signals of the human body. But one function has been missing, which is imaging, right? But we know how important the imaging deep organs is for clinical diagnosis. Right? Now, indeed, so many other groups realize this potential of imaging. For example, Professor Sheng Xi's group are pioneering this field called stretchable ultrasound. They made ultrasound probe to be thin, stretchable, conform more to the human skin, and use that to image deep internal organs. Great progress. So one recent paper on Nature, this is a beautiful paper. But this stretchable ultrasound suffers some intrinsic challenges. Number one is acoustic wave is directional. Stretchable ultrasound probe conformal to the skin, right? Parallel to the skin. Then the resultant imaging direction is not always optimized. You can see for this case, you will miss the major reflection from the acoustic emission. Right? Number two, ultrasound imaging is different from electrophysiological signal measurement. Ultrasound imaging requires accurate transducer position. You need to know exactly locations of each transducer during the whole imaging process. However, when you stretch this ultrasound probe around the skin, right, that induces significant imaging errors. And Sheng's group and many other groups are trying to using modern technology such as AI to address these challenges. My group proposed a different approach. We call it a bioadhesive ultrasound. So here's the key idea. We make the ultrasound probe to be thin but rigid. You can see this is a flat, rigid ultrasound probe encapsulated by epoxy, very robust. It can be reused over multiple times. Then we use a soft bioadhesive couplet. This couplet is a hydrogel elastomer hybrid, literally to adhere this ultrasound probe to the human skin. So you have skin adhesion and the conformation to this bilinear curvature of the skin. Then because we can mold this hydrogel into different shapes, right? Then we can achieve optimized imaging direction, right? You can mold this hydrogel to a wedged shape. Then you can really, achieve the optimized imaging direction of diverse organs in the body. We do not need a stretched ultrasound probe, no image distortion. Then this soft bioadhesive couplet enable functional communication, electrical, acoustic, optical, chemical, biological communications between the machine, ultrasound probe, to the human body, the skin, right? So then with this new idea, now we transform this ultrasound image, something very powerful, clinically very powerful. However, you have to do this, ultrasound imaging currently in a hospital, and the imaging is a snapshot, and you have to be in a static state, right? Laying there or sitting there to receive ultrasound imaging. Right? Now we convert this imaging modality into something like this. This is a wearable. You can wear this at home or in hospital. The imaging now is a long-term continuous. You can image deep internal organs over days. It's hand-free. Now you don't need a hand to hold this ultrasound probe anymore. And you can undergo different types of dynamic body motions because you literally adhere this thin ultrasound probe on the skin. Right? So then some technical details. How can you guarantee this robust adhesion of the ultrasound probe with the skin? Right? We developed this bioadhesive technology over years. So the key idea is you form this hybrid cross-linking, very fast but reversible bonds, such as hydrogen bonding, electrostatic interaction, and strong covalent bonds, such as amine bonds. Then you achieve overall fast and long-term robust adhesion to the skin. At the same time, you make this coupling to be tough, right? Build the dissipation into this stretchy polymer network. Then with that, you can achieve, this is interfacial toughness over 500 joule per meter square over 2 days, 48 hours, right? You can see. And we did the mechanics. The maximum driving force for debonding is on the order of 20 joule per meter square for a rigid, thin device like this. Then you can see this interfacial toughness is much higher than this, debonding driving force, so that it can maintain on the body stably over days. Right? Then with that, we also, optimize the acoustic properties of this Bose couplet because this is a solid hydrogel elastomer hybrid. We can tune the shape. We can tune the attenuation coefficient. So in comparison, right, here others this commercially available couplet, acoustic couplet, all the way from liquid hydrogels, solid hydrogels, and the commercially available elastomers. You can see this Bose couplet has the lowest acoustic attenuation coefficient. Then it will allow the maximum imaging performance, right? Transmit acoustic power from the ultrasound probe to the body and then back to the ultrasound probe. So then in order to design this high performance ultrasound probe, we really thin down the traditional handheld ultrasound probe, but integrating all the key components, matching layer, backing layer, circuits, and high performance piezoelectric transducers. So here we use piezoelectric, transmission technology. Then in terms of the skin performance, you can see the by Apple Watch power is on the order of 100 milliwatts. Bioadhesive ultrasound power is only on the order of 10 milliwatts. Very low power device because this is unifunctional. Apple Watch is multifunctional, right? Then once you wear this device on the body over 48 hours, it maintain same temperature, right? The minimal amount of heat generated will dissipate into the environment. This is the design of the control system, all the way from beam formation to imaging generation, to power, to Wi-Fi, right? So this is a fully integrated wireless system. You can put it in your pocket, use a wire to connect to this thin form factor ultrasound probe. Then this patient is mobile. You can do all kinds of sports over 2 days, and then you need to recharge the battery after that time. Then with that, let me discuss some potential clinical indication for cardiovascular health. The first one is a blood pressure waveform. I do not need give the motivation. John gave a beautiful discussion on the importance of this blood pressure. But currently we know how challenging it is to use this blood pressure cuff to measure the blood pressure. Also, it's very important to measure the whole blood pressure waveform in addition to the two values of blood pressure. It turns out the blood pressure waveform is closely correlated to the carotid artery diameter. With this understanding, now we just simply adhere a bioadhesive ultrasound patch on the neck and then imaging the carotid artery over 48 hours continuously, and then use some simple AI algorithm to measure the diameter of this carotid artery, over time. Then with that, we can achieve long-term continuous measurement of the blood pressure waveform over 2 days. Then not only that, we also have some byproduct. So here is the blood flow rate by tuning this Bose into this Doppler mode, right? So you can see this is blood flow rate at a static state. This is after training. You can see dramatically enhanced blood flow rate, right? What can be the potential impact? This is my systolic pressure over 2 days, right? Literally, you can see after some sports, my systolic pressure, spiked up. And then, giving this talk, for example, I get very nervous. The blood pressure can increase again. Then at this time, my cell phone will send me a warning. Either I should calm down or I should take some medication. You can see there's a closed loop mobile monitoring of blood pressure and for closed loop treatment. The second one is long-term real-time imaging of cardiovascular dynamics. Right, cardiovascular disease is the #1 cause of global death. Right, we know how important it is to measure diverse physiological parameters of the cardiovascular system. Right, for example, Apple Watch made a breakthrough by providing this long-term continuous ECG, right, measurement, and they use AI algorithm to diagnose AI for other potential heart attacks. Right, that's really revolutionary. However, it turns out ECG can only diagnose around 22% of heart attacks. Right, the majority of heart diseases actually require other, for example, imaging modalities for diagnosis. And now we have the capability to have multi-directional views, 48-hour long-term continuous imaging of cardiodynamics. Right? You can see here, I only give you an image every half an hour, but anytime the patient feel chest uncomfortable or chest pain, we can record a short video and send that video to clinician in real time for diagnosis. In future, you can even imagine using AI to analyze this long-term time series imaging data to develop this algorithm for a patient at a normal healthy state and at a diseased state, then for automatic diagnosis. Right. Also, I want to point this out. Heart disease risk soars 63% after the COVID-19, even with a mild case. Right. So imagine the potential impact of this kind of wearable imaging modality on this cardiovascular health. Right. Then just related to COVID, I want to mention this real-time monitoring of the lung. Right. So this is the first time over 48 hours we can long-term continuous image the lung. Right. For example, for anyone test COVID positive, now they can go home, stick a Boss patch on their chest. For the majority of those patients, their lung will look thin proline, smooth parallel A lines. Right? This indicates healthy lung, no lung infection or pneumonia. However, for very few patients, if you observe this irregular proline, condensation of A line, that indicates lung infection, potentially, lung pneumonia, this kind of COVID, effect. Then for those patients, right, the cell phone will give them a warning. They should go to hospital for follow-up diagnosis or treatment. Right. This is much before the blood oxygen level getting too low, because blood oxygen is the consequence, and this lung infection is the cause. Right. So this is really early diagnosis with this imaging capability. Another one is now we can even adhere multiple of these Boss patches around the diverse organs and tuning each of the Boss patch to the ideal imaging direction. Then for the first time, now you can imaging multi-organ correlation simultaneously. So this is another, we work with many clinicians. They really think this can be, a game changer for the field. But now you can, because now you have long-term continuous multi-organ imaging. Right. So here I give you one example. For example, this is diaphragm. For some patients, their diaphragm can lift up suddenly, and that can compress the heart, the right atrium, and then it turns out during this physiological process, your jugular vein, you can see the diameter dramatically increase. Right. So this is the physiological and the mechanical interplay of diverse organs in the body. So here's one summary. You can see diaphragm lift, decrease the right atrium volume, distended the jugular vein. Right. So then this has many potential implications. For example, for this kind of patients, maybe we closely monitor the jugular vein together with a carotid artery for blood pressure. Then if we see irregular distension of jugular vein, we can double check the cardiovascular health. Right. These are the kind of potential impact. Another one is, let's go back to this blood pressure cuff, right? So now for the first time, we can image both the muscle state and the blood vessel state, right? During this, blood pressure measurement. It turns out that during this blood pressure measurement, you actually compress the muscle, but you actually dramatically decrease the flow rate in your blood vessel. For short term, it's okay. But if you want to rely on this for long-term continuous blood pressure measurement, then there can be consequences, right? Just imagine the potential impact of this kind of multi-organ imaging with wearable ultrasound probes. Also, I mentioned this can be under different types of dynamic body motion, right? Jogging, bicycling. This is imaging during sports. I want to emphasize, not after sports, because literally we adhere this ultrasound patch on the skin. The integration is, very robust, so it gives you high quality, stable imaging. Right? So just down to the earth, what's the imaging quality of our current wearable ultrasound? We compared with, state-of-art point of care ultrasound devices, such as a Butterfly IQ Plus, right? So these are the images, we measure muscle, bladder, and the carotid artery and the jugular vein, right? Even, evaluated by professional sonographists, they think these images are with a similar imaging quality. However, bioadhesive ultrasound give you long-term, continuous, wearable, hand-free imaging on dynamic subjects, right? Imagine how you can extend point of care ultrasound into another dimension, right? Long-term, continuous, wearable. Soft materials can be as hard as AlphaGo and the CRISPR, and I have the data to show that, right? This is the Omnitrix score after we published this BOWS paper. You can see it's similar to the first AlphaGo paper by DeepMind team. It's even similar to the first CRISPR paper by Dowden and the Carpenter labs. I think this field of a soft material or this integration of humans and machines has a huge potential, right? Lots of opportunities that we can explore. So not only that, we care about this even more. World's top clinicians and the researchers, including Nan Shu and Professor Sheng Xu, their evaluation on this technology. Here, I give one example, Dr. Eric Topol, our COVID hero. It's a very impressive new frontier about how we can use ultrasound imaging continuous to access multiple organ systems. It's a new window into the human body that we have never had before. This is anatomy. This is very different. We have never had a sensor with continuous anatomical imaging. Right? With that, I want to propose a fundamental challenge in science and technology to conclude my talk. Currently, we can achieve super resolution imaging of single cells. For example, 2014 Nobel Prize is awarded to super resolution imaging of a single cell. However, human body consists of trillions of cells, right? And those cells organize into diverse organs and organ systems, right? Can we achieve long-term continuous imaging of the full human body, right? That will give you a system-level understanding of a human body and the diverse diseases, right? Disease of one organ, whether that will affect another organ. What's the interrelation of a cardiovascular, diseases on other organs of the body, right? And what's the consequence of such intercorrelations? Now with bioadhesive ultrasound, we are beginning to have this system-level understanding. Now within my lab and in collaborators' labs, literally we adhere multiple ultrasound probes on the human body for both healthy subjects and for patients. Then we obtain long-term continuous imaging of diverse organ correlations. With that, we will use AI to analyze and understand those data to develop a personalized digital models for each person at a healthy state and at a diseased state. So then I discussed this bioadhesive ultrasound. The key idea is a thin, rigid ultrasound probe. soft bioadhesive ultrasound couplant, fully integrated wireless portable control unit. Then the result is a wearable, long-term, continuous, simultaneous imaging of multi-organs under dynamic body motions. Acknowledgement, especially our clinical collaborators, Dr. Aman Patel, Pablo Horker, Eris Webbs, Rafael Bano, Franco Lozolfo, Christopher Nabzi, Lehigh Griffiths, Albert Kwong. This is a dream team of clinicians collaborating with us, and of course, fundings from diverse funding agencies. Thank you very much.
Thank you very much, Shenhe, for telling us from the starting of the wearable ultrasound to the latest, even under review work, so that we can get an early sneak peek. So I am going to read from the Q&A box. There are actually two questions, but further elaborate. First, what's the resolution of imaging? And I think you mentioned it is comparable to butterfly, but can you tell us more, like whether the resolution, how important is the resolution for this kind of continuous wearable ultrasound?
That's a great question. So in terms of resolution, it depends on the imaging depth. For very shallow imaging, we can use high frequency. For example, for the carotid artery, jugular vein, we can achieve 100 micrometer level resolution. For deep organs, such as heart, cardiovascular imaging, we can achieve 500 micrometer to 1 millimeter level resolution. But in terms of ultrasound, resolution is only one thing. It's really the imaging fidelity is very important. What matters to clinicians are the most important things, or what can be analyzed by AI. So currently we use point of care ultrasound as the gold standard. We are trying to push the bar to card-based ultrasound. We believe we have some chance, but currently our resolution for diverse organs, diverse frequency, we can achieve the state-of-art point of care ultrasound imaging devices.
Thank you. And the next question is by Alex Jaffe. So they are wondering about the minimum power dissipation required to obtain these images. You mentioned about the power consumption is only 10 milliwatts, but I am not fully clear about the dissipation. Does it mean like how much power is absorbed by the body? I don't know if there is any like safety concern when we have this long-term exposure to ultrasound power.
Very good question. So first of all, this bioadhesive ultrasound is fully under FDA approved power level. It's even lower than the traditional ultrasound power because due to this thin form factor design, and we also need to consider the power consumption for this mobile device. That's number one. Number two. So this is a confusion for many people outside the ultrasound field. For B mode imaging, you only send a pulse of around 1 millisecond, for every second or for every 100 millisecond. So the power, even for long-term continuous imaging, the power emission to the body is very low. As long as you do not generate the heat to heat up local tissue of the skin, then it's safe. Also, if we have further concerns, for example, for pregnant females, for others, very, very sensitive imaging, then we can tune down the imaging frequency. We can image, take one image every, let's say, 1 hour or half a day, but you still have long-term imaging of the organ that you need. It's really about a clinical need. But in terms of safety, especially for ultrasound imaging with a BAL system, we do not have a concern. We work with many clinicians. It's get through the IRB of MIT and Stanford Hospital and the Harvard Medical School quite easily because people understand this power is even lower than FDA approved power level.
Thank you, Shenhe. Thomas, I have one more very interesting question. Can I go?
Sure, please.
Okay. This is from Philip Tan, Xuanhe, who wrote the commentary for your science article. So Philip is very appreciative of your wonderful talk, and he has a very interesting question that for traditional handheld ultrasound, the sonographer has the 5 degrees of freedom, right? They can move X, Y, Z, and also have rotational freedom, plus the beam steering, right? To manipulate the probe to correctly capture the desired anatomy. But with your BAUS, the ultrasound patch, we don't have a human manipulation on top. Is this a significant obstacle, and can it be overcome?
That's a great question. So the title of our new paper current under review is Adjustable Wearable Ultrasound. It's exactly solving this question. How do you adjust and then freeze the ultrasound probe at the desired location and the position so that you have optimized imaging direction? So that's really one advantage, I would say, in comparison with, for example, so-called stretchable ultrasound. Stretchable ultrasound is parallel to the body. You cannot adjust the imaging direction. But with bioadhesive ultrasound, you can do lots of innovation about the coupling. Then you can tune the imaging direction and then freeze at the desired state, and then image the at optimized imaging direction.
Do you mean human?
Human, yeah. The manipulation is still by human.
Okay.
Yeah, so that's still by human. But currently, there are some AI algorithm will tell you when you achieve the optimized imaging direction. Those algorithms already become mature. So there are even companies, selling those algorithms to ultrasound companies. So that will be the next step. Couple that hardware with those algorithms to really give people, experience free or this user independent imaging.
Great, thank you so much, Xuanhe. I will hand over to Ruth.
Thank you. Thank you.
Thank you so much, Dr. Zhao and Dr. Liu. It's my great pleasure to introduce our third speaker, Dr. Stephen Steinhubl. He is a career-long clinician scientist and the Vincent Riley Professor of Biomedical Engineering at Purdue University. Prior to returning to Purdue, he was the founding director of Digital Medicine and the Scripps Research Translational Institute. He remains clinically active as a cardiologist and serves as the consultant chief medical officer for the health data analytics company, Physic. He received his undergraduate training in chemical engineering from Purdue, medical degree at St. Louis University, and cardiology training at the Cleveland Clinic. His research centers on the development of individualized digital biomarkers made possible by wearable sensors, as well as implementation of health research and care programs built around the unique capabilities of full range of digital health technologies beyond sensors, including AI-based analytic insights and precision communications to provide personalized real-time value to individuals. A particular focus of his digital solution building is for addressing long-standing disparity and inequities in healthcare and the lack of diversity in health research. He's a faculty champion for infectious disease for Purdue's Health Equity Initiative. Steve has been the principal investigator of dozen nationwide and global clinical trials, has published around 300 peer-reviewed articles, and was the founding editor-in-chief of Nature NPJ Digital Medicine, Nature Partner Journal Digital Medicine. He is also the occasional breakfast cook at his wife's B&B, Sustina's Place at Anchorage, Alaska. I need to visit. Dr. Steinhubl, please go ahead. We look forward to your time.
Thank you very much. Thanks for including the advertisement for my wife's bed and breakfast at the end. So first, let me say it's a huge honor to be presenting, and especially presenting after John and Xiuan He, because their work has inspired me, and I think is going to help millions of people and has moved the field forward. Let me before I start, let me just these are my conflicts of interest. As mentioned, I'm the chief medical officer for PhysIQ and have been an advisor for these companies over the time. So anyway, the previous two talks, and I think the talks in the last several days in looking at the agenda, is just an amazing capabilities. And so I kind of took the liberty as a clinical perspective, because I was recently motivated by an article I read that I'll show you. So I'll start back in this article from 1970 about medicines and the computer. So it was the early age of really what's the promise of digital capabilities, in this case computer, but all digital. And as you can see, it says, one may hope that the computer will help free the physician to concentrate on the tasks that are uniquely human. So that was really, from the clinical perspective, what the hope was for digital technology, and I think is still the hope for digital technology. The article I saw that made me go back and look at this is an article from a little bit over a month ago on digital minimization, a prescription for clinician burnout. And compared to that 1970 look, this says digital tools play a big part in making the experience of being a clinician overwhelming. And it has the use of digital tools, in this case, look at EHR use, has correlated dramatic declines in clinicians' time at the bedside. So this kind of juxtaposition of what everybody saw, and I think everybody in these calls and in this meeting see, is what the capabilities of how digital technologies can really improve care, can make healthcare from a clinical standpoint much more human, have instead had the opposite effect and have led to a significant burnout of clinicians and not the major changes in care. So I'm going to take the liberty of kind of focusing on that as to why is that the case. So we'll talk a little bit about the current reality of where digital technologies can and how they're slowly making inroads. And I should say I'm going to mainly focus on the outpatient aspects of it. There's been tremendous changes in my career, my almost 30-year career now as a cardiologist, in inpatient care and acute care, but less so in the management of keeping people healthy as an outpatient. So I'll start with this current reality and mention. So I did my cardiology training, started in actually 1994. In 1996, the ACSI Red was the world's fastest supercomputer, was the first with teraflop speed, had used electricity of about what it would take to run 800 homes, and cost about $67 million in today's cost. And then you compare that to today, Samsung Galaxy is an example, 1.3 teraflops of speed, about 0.4 watts, and about roughly $900 to $1,000 US for that cost. This is, laying this out, is how the environment has changed of what our tools are, of how we can better take care of patients. Another big change, besides that computational power we hold in our hand, is the connectivity. So these are data from Pew Research, I believe from about 2020, or the data published in 2021, just showing both the combination of smartphone use and home broadband that have broadband continuing since 2000. I think the first smartphones really around 2007. But if you look combined, about 91% of all US adults have access to either broadband or smartphone. So have this continuous connectivity of the capabilities of really doing providing technologies or advice, guidance, care as an outpatient that was nothing like what I had available in the mid-1990s when I started my training in cardiology. As another example, when I was lucky enough to join Scripps Research with Eric, and thanks Xuan He for showing Eric's picture in 2013. At that time, the wearable sensor, at least the consumer side, the kind of state of the art was the Fitbit Ultra, where it measured activity by clipping it onto your belt loop. And if you wanted to download the data, you plugged it into your computer and were able to download it. In 2020, Fitbit had the Fitbit Sense, where you had activity, sleep, heart rate, respiratory rate, heart rate variability. You could get a spot EKG check, you get electrodermal activity, temperature, and SpO2. None of these in an FDA regulated, or I would say well-validated way, but from a consumer standpoint. an incredible step forward compared to less than 10 years earlier, what the Fitbit consumer device was able to do. And now today we have devices. An example is the BioBeat that out of Israel that has blood pressure, systemic vascular resistance, cardiac output, temperature, heart rate variability, respiratory rate, SpO2. And unlike the Fitbit device, actually does have regulatory approval for those devices in the U.S. I believe it's the only pulse waveform based FDA approved device in the U.S. And when you look at what these capabilities are, so continuous blood pressure, continuous cardiac output, continuous systemic vascular resistance, this is really the only other setting where you get that kind of information. So the capabilities of wearable sensors and how quickly they've progressed, and they're certainly, we haven't reached a plateau. We're going to keep getting better. And because of the work that you've heard about in the hour before this is the reason why. We're going to be able to take care of patients, outpatients, or manage and keep them healthy using technologies that really even today we can only have when somebody is in an intensive care unit with an invasive monitoring technology. So we have all this technology, and then let's see, how are we actually implementing that in care? And this was an article from last year that just did a very simple look at electronic medical record data in 500,000 people and looked at, compared between 2005 and 2019, the mention of any wearable technologies the individual used for their healthcare. And you notice from the graph that there was a substantial increase, but it started low. So it started at 0.0002% of mentions in 2005. It increased up to 0.89% mentions in the electronic health records in that. So an optimistic view is you had a 4,500-fold increase in mentioning these technologies, people using these technologies to monitor their health or improve their health. And this is a very low bar, just mentioning it in the record. Whereas the pessimistic view is at this even with this very low bar, less than 1 in 100 visits ever mentioned the use of any kind of wearables technologies to improve care. And then I'm very involved in clinical research and feel at Scripps, our main focus was really on using wearable technologies to break down a lot of barriers in healthcare, or using all health tech technology. And so you would think with the change in technology, there'd be this dramatic increase in using digital technologies in the healthcare. And actually, this is data from global data, and just shows that the percentage of trials that use any kind of virtual components of health technology to capture data increased from only 1.3% in 2011 to 3.5% in 2021. Now, that did correlate with less trials being suspended or terminated. That's I'm not sure if that association is real, but still, we have a long ways to go to really take advantage of what these digital technologies can allow us to do. And then the last thing where we stand, and kind of going back to those original 1970 and 2023 articles of the promise of computers. This is a Medscape review focused on cardiology, lifestyle, happiness, and burnout report. And this is the bottom line finding that just over half of cardiologists consider themselves burnt out and or depressed. And this again goes back to that need of a digital holiday. And again, a lot of that focuses on the electronic health record, but it's really just around the system of care, which will lead into my next area of discussion, that is not really taking advantage of digital technologies, and rather just increasing the burden to cardiologists and other physicians. And so to me, that is where the potential is. And I'm going to turn to this potential into how do we turn this into the future reality? So when we think about what the promises of digital health technologies, it's important to recognize that everybody, I think everybody from a leadership standpoint in healthcare and a clinical care standpoint, sees it as being the future of healthcare, right? I'll give some examples. This is just from a paper from the National Academy of Medicine, just talking about what all the potential is for digital health applications and how we can improve care using those applications. Eric Topol led a group as a leadership in the National Health Service in England that talked about preparing the healthcare workforce to deliver the digital future. The World Health Organization has a global strategy on digital health and how digital health is it can impact care and improve our care. And then we have the American Medical Association looking at the future of health and closing the digital health disconnect, a blueprint for optimizing digitally enabled care. So from a care provider standpoint and overall, there is a lot of enthusiasm. It isn't like there's barriers to say, no, we shouldn't be using digital health technology. There's that support is there from the highest levels. But I think that the biggest barriers we've had is that most attempts to improve healthcare using cardiovascular health technologies have been by trying to incorporate them into existing systems of care. And I'll get into that a little bit more. I think instead the solution is that our goal must be to build new patient-centric systems of care that take advantage of the unique capabilities that cardiovascular and all health technologies offer. And I'll show this in use an analogy going back to what's been called the productivity paradox of when we transitioned from steam engines in manufacturing at the late 1800s into electricity. So up until the late 1800s, the only power source was steam engines. Steam engines, as you got further away from that power source, you lost more and more energy. So factories that needed power put all the manufacturing processes needed as close as possible to the steam engine, above it, below it, next to it. It didn't matter. You needed the energy. The productivity paradox came from the thought that, oh, well, electricity will make a big difference here. And manufacturers started installing electric dynamos and using electricity to take the place of the steam engine. But what it found is it didn't really have a significant impact on productivity. This is a graph from The Economist just showing that, and it's hard to tell from here, but if you look at where electrical generators start, there's a very minimal increase in productivity. It actually wasn't until several decades later where you saw this really jump and change in productivity in the use of electricity. And when that happened is when individuals such as in automobile manufacturing and the assembly line, interestingly, cigarette manufacturing was a leader in this too, took advantage of this technology, this new technology, electricity, and said, we can completely redesign our systems of manufacturing to take advantage of what this new technology does completely differently than what a steam engine does. It gives us power, the same amount of power a mile down the road as it does right next to the device. So let's redesign our systems in order to take advantage of that technology. And I think that's very similar to the way we have to think of our health technologies in medicine. So that our steam engine model is shown here, purposely picking a doctor with their back to the patient while they're entering data in the electronic health record, because I think that's very appropriate. So that's the steam engine. And now there's been a lot of enthusiasm around virtual care and telemedicine. But really, to me, that's just using technology to add into what's an existing system of care. It's still focused on this episodes of care, and episodes of care are designed around, frankly, me and my schedule. So when I see a patient for heart failure and they're doing okay, I'll arbitrarily say, okay, I'll see you in 3 months or 6 months, or I kind of will make it up and at the time. And then in between then, it's kind of, you keep your fingers crossed and hope nothing bad happens. And if they start feeling poorly, they can either call and maybe get squeezed in for an appointment, or more often than not, they end up in the emergency room. It's really still, even though with virtual care, it's still built around these episodes of care. I think what the new taking advantage of the digital health technologies and the state-of-the-art sensors and what we can monitor individuals as an outpatient is really this the innovative aspect of building new systems of care, where what this individual has shown right here is this is what healthcare should look like. It should be a passive capability of taking care of somebody with the wearable sensors, with maybe an in-home acoustic sensors, with the capability to text or ask a question if needed, or get a two-way response, or if a phone call's wanted. And that in the back end, that there is a kind of passive monitoring mission control center that is able to see any and act upon any deviations in care, or be able to answer any questions when those questions arise. And some of those questions are going to come up 24/7, and there has to be that capability. And I'll talk a little bit more about that, because to me, that can often be one of the biggest challenges in healthcare setting. As I mentioned, healthcare, since the beginning of when individuals went to see a healer, is based on these episodes of care, and what our connectivity and our use of smartphones and the computer is really what changes that dynamic. So if we're going to take advantage of digital health technologies, right now, almost all of them default to, and if you have any questions, go see your doctor, or if you're concerned, go go to the emergency room. But we're offering this care often using a smartphone that on average a person touches over 1 million times annually, and on average will go through about 2,700 per day. My children, by the way, are major contributors to that 2,700 per day. Data from iPhone users, they unlock their device 80 times a day. That's an average of 6 to 7, every 6 to 7 minutes in a 12-hour waking day. And then when they unlock that device, based on the earlier data from nature, they obviously go through multiple pages at that time. In Google, we know that there's over 70,000 health-related Google searches every minute. That's greater than 1 billion a day overall. And about 1 in every 15 Google searches are health related. So there's this, the patients we want to take care of are not satisfied, or we're not going to create a new healthcare system that's based on go see your doctor or write your doctor if you have any question. We have to be able to create solutions that can answer their needs 24/7 whenever they want to, through this two-way communications. And the challenge with that communications is that there is not a one size fits all. And that's also one of the challenges that we need to overcome. And what historically we've done in healthcare, when we use digital technology, we'll offer, oh, you got a question about a heart attack? Here's a general teaching about a heart attack. This is an example of a really nice study that just looked at the differences in communication and what's important. And again, a little bit of this looked at genetic information and the like, but the investigators broke down various information that patients or research participants might like based on their educational attainment. And they looked at, shown on the left-hand side is what individuals saw as least valuable information. On the right-hand side, look at what's most valuable information. And what is interesting is when you look at how the one question about how genetic information might affect your medical conditions, it was considered the least valuable in those individuals had a high school or less education, but it was considered the most valuable information in individuals who had some college or college graduates. And so any kind of communication solution, it really has to be personalized to that individual. And to me, again, I've been, as I talk about digital technology for the last 10 years, I've always thought that was the biggest barrier. I still think that's the biggest barrier. And what has really been transformational in the last, more publicly in the last year or so, but obviously ongoing before that, is the capabilities of generative AI and conversational large language models in healthcare. And these are just 3 recent papers of ChatGPT passing the medical boards. Another on ChatGPT passing the neurosurgery oral board exam. So the same exam questions that somebody with 7 years of neurosurgery training after medical school, plus 3 years of clinical practice would be asked. And they asked, and then a paper from last week that looked at ophthalmology symptom triage and the performance of a large language model in effectively acting as a triage model. And that offers amazing capabilities in that digital health environment and building that new systems. This is one last paper that was published, I think, in the last 2 weeks that looked at AI responses to a little bit less than 200 medical questions, and they compared that to healthcare professional responses. This is on a subreddit, and they compared those healthcare professionals blindly compared the responses and graded them based on quality and empathy. And you'll see by the graph there that the chatbot, the ChatGPT, this case, outperformed in both quality and empathy, and that overall the AI responses were preferred to the physician responses almost 80% of the time. So this offers a capability. Obviously, there's many limitations and a lot of stuff to work out, but I think this will help us overcome some of the biggest hurdles of creating new systems of care that are built around these health technologies, or take advantage of what these health technologies can allow. Now, I don't want to make it oversimplify it. It requires a lot of infrastructure. This is from that same National Academy of Medicine paper, just showing kind of what's needed. And then this just highlights, the kind of failed attempts at many big health tech firms that have gone in to try to answer this. And so obviously there's a lot of challenges and a lot of thinking differently that's required to create the infrastructure needed to provide these new systems of care that take advantage of the digital health infrastructure. But these are 4 examples of companies that have been developed around providing digital first care solutions for cardiology as a primary focus: Heartbeat, Homeward, Story Health, and Mega Health. All of these are designed to take care of patients with cardiovascular diseases and manage their conditions in their home. And so it's a good starting point. And there's going to be more and more that are developing in the future. And I think this is what's going to really help change the clinical use of a lot of the great technologies you've been hearing about in the last 3 days. So in conclusion, I'd say that despite a growing collection of personal health technologies that have the potential to substantially improve outpatient cardiovascular care, clinically, there's really been very little to show for that on an outpatient basis. I think it's critical that we incentivize creators to build these new systems of cardiovascular care. Some examples I showed earlier that are designed to reach and meet the needs of all people, and that enable providers to better focus on the human needs of patients. So I want to thank everybody for their time and for the opportunity to present today.
Thank you so much for the wonderful talk, Steve. I am going to go over some of the questions. So first question is, the key challenge is to reduce this multitude of wearable patient data and other clinical data to actionable events. Otherwise, the added oversights will require more nurses and continued burnout. This was a comment. Thanks for the wonderful talk, Dr. Steinhubel. From your talk, it's clear that digital health already provides extremely valuable information to patients and physicians and will be even more transformative in the years to come. From a patient perspective, what do you think the largest obstacle, for example, adherence to device attachment, will be in adopting digital health technologies, and how these can be overcome?
Yeah, it's great. And let me, the biggest obstacle, I think, is going to be the creating value for the participant, right? So I'm a big believer, and I had a patient teach me this like a week after I was done with my medical training on practicing my own, that people don't like being reminded they're sick. right? And a lot of healthcare solutions, we say, oh, you just have to measure this, or you just have to wear this device, or you just have to, sit down quietly and do an EKG twice a day, or and we have to create solutions that provide the individual value and value to the point where they say, okay, I want to wear this device because it brings me, there's value, there's information that I can get something out of this, or I'm okay, doing this once a month in my house because there is value to that. And so far, much of the solutions we've created and the wearable devices have really been around have not been built around patients or individuals, but it's been built around, here's the information doctors would like. And that's important, obviously, but there has to be that combination. And if we want the patients to wear it, we need to. I'll go back. The other big challenge I think we have to, and Juan E showed this, and in his, I like that the blood pressure changes with talking and exercising and stuff. I would say, we have to realize this is almost like a brand new vital sign to clinicians, because no one can tell me or tell you, what should your blood pressure be when you're stressed, when you're talking? Should it be 150 over 90? Is that normal? Is that okay? Or are you healthier if it stays at just 120 over 80? And so a lot of these data, and we use the example, there was a lot of COVID data that showed small changes in heart rate is predictive of a COVID infection, which is really great. But just even that, that's very personalized data. And in the sense that, everybody on this call has a different resting heart rate in the heart rate that responds in different conditions. So you have to know that this person's resting heart rate is normally 62 and right now it's 82, and that means something bad is going on. But the healthcare systems and what we have no, we just look at, does it fall somewhere between 60 and 100, and then if it does, it's okay. So we have to look at this, and a lot of the data that the healthcare technologies that these technologies provide is new information and new personalized information. And so there's still a lot to learn about it. So it isn't just a kind of, we're going to plug in and replace what is routinely done with something more convenient. It's really new information and new, really valuable information. So it's incumbent upon us to find the solutions to take advantage of it.
Thank you so much. Next, possibly the last question, so we can enter the panel discussion and we would have live conversation. A great perspective, Dr. Steinhubel. Can you please speak to the challenges of affecting the regularity and payer incentives, that is the overall U.S. health existing infrastructure from a bottom-up effort by digital health, or do you actually have to change for digital health to be widely successful?
It's a great question, and probably a symposium in and of itself, because so from a regulatory standpoint, I would say, and John and Joanie can have more experience that, but I think that the regulatory side is trying to incorporate more digital endpoints, and the FDA has said that and the like, and as I showed earlier, there's a lot of enthusiasm worldwide to do that. The reality of healthcare in the United States today is healthcare systems make money when people are sick. They don't make money when people are healthy. And what transformational digital health technologies incorporation is designed to keep people healthy. It's designed to keep the heart failure patient outside the hospital, and it's designed to be your best you and test at home and the like. So there's making this very painful, slow transition to value-based care. In the U.S., employers have the biggest financial burden in healthcare. They have the biggest financial incentive to keep people healthy. Even payers, health insurers, on a year-to-year basis want to spend as little money as possible, but from one year to the next, they don't care how much healthcare costs go up. They make more money as healthcare costs go up further. So I think a lot of the solutions will come out of low resource areas, maybe in the United States, maybe outside the United States. And as those models are proven to be effective, I think will become more and better incorporated. I think in the United States, the biggest drivers of that is going to be employers who want to take advantage of that.
Thank you so much. So Dr. Help, is this okay if we enter the panel discussion?
Absolutely, yeah.
Okay. Again, I'd like to thank our distinguished speakers, myself, Dr. Nanshulu, and Dr. Health, who are going to lead the panel. I will ask the first question to all panelists. So as you all articulated on the concept that this area is moving forward for an impactful translational solutions. The world needs solutions. It requires engagement of all stakeholders, engineers, computer scientists, health science researchers, even policymakers, end users, care providers. So if you might share with us a little bit about some of your experiences, and especially the challenges that could be addressed by us or by the larger community when we start building all these larger stakeholder group, please. Maybe we start with Dr. Rogers.
Yeah, it's a great question. I'll share some of my thoughts, but I'd love to hear from Steve and Xuan also. I mean, I kind of live in an academic world, obviously, and so that's kind of my environment. And the challenge there is, how do you take a new sensor developed by a grad student, in many cases built by hand, tested in 1 or 2 patients, and how do you kind of scale that to provide the basis for doing meaningful pre-pilot studies, in a hospital setting where nurses are engaging with the devices, patients, and so on. And I think, the federal funding landscape does a pretty good job of, supporting that initial foundational work. But there's kind of a gap, between when a technology is ready for commercial level investment and maybe launch of a startup, and that initial academic demonstration. And so I guess we're in a somewhat fortunate position in the sense that we've used philanthropy to kind of fill that gap. But I feel like many other groups in universities are sort of constrained by how quickly they can mature technologies to eventually get them on track where they can have a meaningful impact on patient care. And I think that's an important consideration, and maybe NIH or ARPA-H, maybe some newer agencies will come into play and be able to address that opportunity to accelerate development of new technologies. Because I think until it's in the hands of patients or nurses, you really don't know what you have. As an engineer, it can work really great when the grad student's operating the thing, but there's so many different user factors. And I think Steve kind of touched on this. I think, patient compliance is ultimately going to determine the utility of any of these technologies. People don't want to use them for one reason or another, then, it's impossible for them to have an impact. So that's maybe one small piece of the broader puzzle that you're describing, but it's kind of the world that I live in and think about a lot. I think we're also active in startups and things of that sort, but I think others could also speak to those challenges. So just one thought to share as a response to your question.
Thank you so much. And Dr. Zhao, would you like to share your insights?
Yes, I truly echo John's comments. So number one challenge for us currently is how to scale from 1 to 1,000. For clinical tests in hospitals, right? Yeah, both from the funding mechanism approach and from the just the manufacturing approach. So that's one challenge. Then the second challenge is once you deploy these devices in the hospital, right? How to guarantee the performance of nurses or sonographers. Similar to the level of what we operate in the lab. So this user dependency become a big issue currently for us. We are developing some technology to address that. Then the third one, John didn't touch this point, but for us now the data. So some audience also ask this question. We can easily accumulate on the order of terabytes of imaging data per day. How to analyze those data? Currently, we do not have ready infrastructure to analyze those data. But on the other hand, those data can represent certain values, right? Because now you have this imaging, long-term continuous time series imaging of different organs of the body. So how to analyze the data, how to protect those data, right? Eventually, how to cross-reference, how to compare one's data with another person's data. So these are current challenges we are facing, but I'm still positive. Here's a very simple reason. Cardiovascular disease is the #1 cause of global death, and in foreseeable future, it will remain to be #1. We have the stake is very, very high, and obviously we need a new technology, to help address this challenge. And the new technology, already show the potential revolutionary power to address this challenge. So I think, all the way from funding agency to researchers, clinicians, and even to the society will work together to, push those technology into, real clinical impact.
Thank you so much, Dr. Steinhubel. Anything to add, please, sharing your...
I would add just two small, totally agree with both answers. And I'd just say that it really depends on what you're creating and what problem you're trying to solve. So for individuals who get care within the hospital, I think finding that champion to work with and things is great. I think when the challenge, I often find that healthcare systems can be not purposefully, not good, but the biggest barrier to anything that you want to implement from a large scale outpatient setting to see if you can impact care. And where I found another funding source that we found in that has a great interest in keeping individuals healthy is DARPA and DoD in trying to use sensor data to detect when a soldier has been exposed to, let's say, a chemical or biological threat. And so identifying that earliest signs of decompensation. So for the things that are most exciting to me of keeping people healthy, I've found the DoD to be a great source of funding.
Thank you so much. Dr. Liu, would you like to take it from here?
Yeah, thanks, Ruth, and thank our panelists. There is another great question in the Q&A by Alireza Gorjati. Great presentation. How can we ensure that technologies being developed are solving essential problems in the healthcare industry rather than being created for the sake of technology advancement? And how can we strike a balance between promoting innovation and ensuring that technology is solving real medical problems? Who would like to take the first step? Maybe Steve.
Yeah, I'll start. So I think it's a great question. And what I always tell people I've worked with and people in my lab is the great thing about healthcare is that there are so many problems to fix that it's not hard to find problems to address. But I think once you identify something, and a lot of times I've had colleagues that have identified things based on their personal experience and is you have to look at who is the problem? Who are you trying to solve the problem for? Is it for patients? Is it for providers? And then, looking at that and talking to the right people. And often, I'll say that, every doctor will feel a little bit differently. So having one clinician's feeling about how a solution works is one clinician's feeling only. And so you have to get a few, but patients in particular, and I like, technologies that are geared towards patients, is really getting input from the individuals that you really want to eventually use this solution. I think that's it. You have to start from that. And frankly, that's one of the reasons I'm at Purdue and in biomedical engineering is to work with students and faculty along that. Because when my time at Scripps in particular, we'd have engineers who would come and they'd come with their completed solutions and saying, hey, here's this. And you look and say, well, the idea is great, but no one's ever going to use that. And it's, and so starting and thinking about not the physiologic problem or the medical problem you want to solve, but what is the true patient or provider problem you want to solve, and then create the solution around that.
Thanks, Steve. John, would you like to comment?
Yeah, I mean, my comment is we need more people like Steve and Eric Topol and, clinicians with a technology fluence, that allows them to interact with engineers. I think the danger is engineers get stuck in the lab and they're cooking up fancy technologies that really don't intersect with any kind of meaningful, need, I would say. Yeah, I guess our approach, and this is not necessarily the right approach, but the strategy that we've taken, and coming back to the balance between innovation and technology that solves problems, I think you need to try to do both. If you're developing an academic research portfolio, a little bit of far out exploratory stuff is great. You never know what's going to happen there, but I think being embedded in the clinical community and understanding what the unmet needs are and how new technologies could address those needs. I mean, our practical experience, and no offense to you, Steve, but the nurses are the best people to work with.
Yep, totally agree.
They know exactly what's going on, and sometimes the physicians do, sometimes not. So we have working sessions with nurses and do brainstorming and stuff, and they're great people to interact with. But back to our strategy, and again, I don't want to put this forward as the ideal, but to start with improved capabilities in measuring parameters that the clinical community already understands. I mean, I think if it's a totally novel metric, it takes tremendous amount of time to understand how that really connects to disease state. And so we've tried to, reproduce data streams that, have established utility and from which physicians can develop actionable insights. And then once you have a foothold there, then you can start adding sort of on top of that set of sensor modalities, things that are measuring more unique or unusual parameters that you feel might be related to health status. But I think if you show up with a sensor that's measuring something that nobody's really ever thought about or understands how to interpret, you're probably not going to get very far. But at the same time, you sort of need that kind of innovation to drive progress over longer periods of time. So we've kind of adopted a bit of a staged approach to develop momentum around things people understand, but then add to that set of capabilities over time.
So maybe I can chime in here and say the question beautifully, sort of crystallized out the technology push and the clinical pull, right? There's oftentimes impedance mismatch between the two, what the clinicians really need in order to solve a real clinical problem versus what we as technologists, like to keep us busy with in the lab in terms of cool technology. We've had probably 10 plus 15 years of ECG patches, right? Yet they're not integrated into clinical care. Has been a heck of a lot of work, including by the people here presented today on arterial blood pressure measurement, and hypertension is an epidemic, if not a pandemic, right? Yet we don't have these systems integrated into the clinical care or routine clinical care. The question maybe to the panel is, if we take a concrete clinical disease state in the cardiovascular space, which one do we really, as a technologist or as technologists working with clinicians, do we have a chance of really addressing or really changing the needle in terms of reducing morbidity and mortality, or just helping our clinicians take better care of their patients?
Well, I'll start, and because there are time, but I think I can't remember who mentioned it, but blood pressure, high blood pressure, something that we've been able to measure for 140 years, something that we have, have treatments that cost less than pennies a day, is the still globally the #1 contributor to early mortality and morbidity. That could be huge, but it's kind of seems boring sometimes. But it's hugely important. And it's also a disease that's the most common chronic condition, and we have like one phenotype for it. Essential hypertension is 98% of the people, and so we treat people very algorithmically. So I think there's incredible technology that can help us better understand and refine the phenotype for individuals with high blood pressure, and then we can create these better systems of care that can address that. I'd add to that, it seems like everybody wants to solve heart failure, and that's a very important thing to solve. But it's a great example where engineers, we look at it from a physiologic standpoint. Well, it's just fluid overload, and we'll do this. But it turns out that a lot of the heart failure readmissions are due to social determinants of health, and there are challenges. That technology often, or at least the technology is designed to track physiologic changes, don't address as well. But I think there's a lot of room. It's just that the solution is not going to be maybe as purely physiologic in heart failure. Anyway, but blood pressure, I should just stop with that.
And how do we integrate those data streams into the clinical care environment to make sure that our clinical colleagues are not overloaded?
Yeah, well, so I think that's the key, and I think I feel passionate about this. You don't integrate it within our existing systems of care. You create new systems that are built just to take care of chronic conditions of diabetes, hypertension, other things, and because the data shows this is more in primary care doctors, that it takes a primary care doctor to do everything they're supposed to do every day, 27 hours in patient care. That the average clinician spends 2 to 3 hours of their personal time once they get home at night, again, primary care doctors, completing their electronic health record. So there's nothing you can integrate in current systems unless current systems develop kind of a technology adjacent or current standard of care adjacent solutions that are really built around all the needs of an individual to track these data streams, and it takes expertise that we don't have. And I want to reinforce what John said. It has expertise that a lot of nurses have, and we never ask the nurses enough to do that. But the nurses, the behavioral economists, the user experience, the communications experts, that kind of expertise is needed to build that solution.
Xianhe, would you like to also comment on this technology?
I think John and Steve give a great summary. My opinion is probably two ends. One is at IC or NICU. John gave a great example on NICU application, right? So intensive care, right? At those places, we need more monitoring for sure. Whether we save the data or not is not critical, but if we can quickly let the nurses or clinicians know abnormal symptom, that is important. So just by our own experience, the potential first clinical application is in ICU. Currently, the clinicians tell us we don't need to save the data as long as you can play the video of the cardiac dynamics on a screen after heart surgery over time. That's can be a game changer. They don't need use a probe to poke the patient frequently anymore. So that's I would say that can be one opportunity. Then on the other end, echo Steve's comments. Really, let's treat the disease before it getting too severe, right? For example, blood pressure, hypertension, right? Can we have a closed loop system, right? We monitor the blood pressure at the same time, give a person warnings, either to take medication or to take some medication, to regulate the blood pressure. That will be, just a new paradigm. But I think the technology are getting mature. Right? We see John's, results and measuring blood pressure from imaging, ultrasound imaging. So I would say this can potentially make impact on two ends. One is very severe condition ICU. The other is at home. Let's treat not a severe disease.
And I would like to add that currently, let's take the non-invasive continuous blood pressure as an example. There are still very deep scientific questions that require scientists and engineers to answer. For example, now we have this new enabling technology of continuous imaging, and we can measure anatomy as well as hemodynamics. But even with all those information, can we still have a more accurate model that can give us the true blood pressure? Even the ultimate dream is without calibration. That's still a very outstanding, profound scientific question.
Yeah, Nanshu, I truly echo this point. Right? Why does blood pressure matter? If we can, directly measure some other signals, right, more critical to health, then we just use that signal, right? Currently, blood pressure, we use blood pressure because it's easy to measure. But if we can have some other means to measure more relevant, physiological signal, maybe we just rely on that. I truly agree with you, Nanshu.
I agree with you too, but you would have to redo a whole lot of randomized controlled trials, right? You would have to change the care of cardiology completely.
Yes.
And now Steve is advocating a new healthcare system that's sort of parallel to what we have, and you're advocating completely, new parameters. I agree with both of you, but we will not change the needle on healthcare if we follow this in the next 10 years, right?
So blood pressure is still the
blood
holy
pressure will still
grail,
be
like
very
John
important.
said. Yes.
It's just that we have to get it right.
Yes.
Because if you're looking at it, between normal tension and pre-hypertension, we're talking about what, 5-6 millimeters of mercury, right? So and what are the corner cases? What are the things that what are the spikes in blood pressure? John showed the comparison to the Finapress, right? Which is not a gold standard by any stretch of the imagination. But what I noticed is that, in an N=1 that you showed, you underestimated the spikes in blood pressure to 160 millimeters of mercury in systolic. That's exactly what the clinician wants to see, right? If this is real, right? So I agree that there's a lot of scientific questions left over. But maybe one other question to Xianghe. Patient acceptance really depends on, as we mentioned earlier, on form factors, on not having some big device with huge batteries that you have to carry around. This work on either stretchable ultrasound transducers or the less stretchable ones with hydrogels that you've done is really fantastic. In all the work that I've seen is that they're still attached to a Verisonic system at this point. It seems to me that the packaging of the electronics and the front end sensing technology is really the critical step here to get to the form factors that you need in order to slush the bytes around that you need in order to bring the power consumption down and to address one of the earlier questions for data storage, right, and data transmission. So where do you actually see this developing over the next 5 to 10 years?
Thomas, in the new paper I mentioned, now it's miniaturized to a cell phone size control unit for both beam formation and image processing, and then you transmit this image real time to your cell phone or your computer, then upload to the cloud. So that is, I would say, even relatively mature because we can leverage state-of-art ultrasound technology, right? All the way from butterfly, Lumify. This is not something difficult. So that's already mature. Currently, the challenge is, you mentioned this, form factor acceptance. That's true, but I would say user dependence is the major challenge for us because we are now trained sonographers how to obtain the high performance imaging across the users. We are working towards that direction.
All right, I'm looking forward to reading that.
Sure.
Are there any final remarks from our panelists? What's the future? Where are you
Yes.
going?
Maybe we'll
Maybe
start
starting
with
with
Steve.
John. John, you
yeah.
mentioned a closed loop sensing, diagnosis, and treatment. I see that to be a very exciting future. How about we can treat our patients before even they know they are ill?
Yeah, I think that's certainly an exciting future, but maybe to kind of introduce a additional topic into the discussion. I mean, pretty much everything we've talked about so far has been in the realm of biophysical sensing, but biochemical status is maybe as important, maybe more important in many cases for patient care. And so, what can you do in the world of wearables to characterize blood biomarkers, for example, and what sort of, biofluids are accessible in a non-invasive way that would allow for that kind of monitoring. We've been interested in sweat, for example, a number of other groups, but, CGM technology, I think is extremely exciting. Could you develop a CGM type platform that does a full panel analysis of blood biomarkers? And could you do that continuously? I think that would be radical technology that would have massive, uses. You could track, blood creatinine, for example, blood urea, in kidney transplant patients, looking for early signs of rejection. There's just myriad applications that would follow from that. So maybe kind of a grand challenge, certainly something that we're thinking about is how to qualitatively expand beyond the kinds of parameters that current wearables monitor to the realm of biochemical tracking.
Thanks, John. Steve?
I would, John's answer, I mean, that's always inspiring. Obviously, a lot of solutions be built on what the great work that others like John are doing. But, I think that the future is, we talk a lot about precision medicine, and usually when we talk about it, we're referring to genetic information. But what the sensor technologies allow us to do is to really create true individualized medicine, so that, you look at everything we do now, blood pressure, heart rate, respiratory rate, temperature, they're all based on a population norm. They're not based, any clinical decisions are based on how your measurement falls within that population norm. And we can do better than that with the sensors. And so no matter what the sensor technology is and the capabilities, it's really refining our knowledge to provide more individualized solutions that we've never really had the ability to do before. And there's a lot of challenges, but incredible opportunities for that.
Brilliant.
I really, echo what John and Steve commented. Chemical sensing, especially minimal invasively chemical sensing, beyond continuous glucose sensing. Then I want to add one point is data analysis. Now we have access to huge amount of data, how to analyze, understand those data, and how to protect the privacy, based on those data. So these will be questions that we'll think about.
Right. On that note, I would like to take the chair's prerogative here, and I would like to close the session by, again, great gratitude to all of our speakers and co-chairs, not just today, but over the last 3 days. And thanks to everybody here for the great discussion. And I'm sure that, with the right combination of technologists, clinicians and industry in the room, that we can bring really the technology to unimaginable heights in cardiovascular health tech. Thanks to the audience, for everyone for the 3 sessions, for making this conference immensely popular. We had close to 300 registrants over the past 3 days. The videos will be made available to those who are registered for all 3 sessions. And we hope that this conference will inspire further progress in the overall cardiovascular health tech field, inspire future in-person meetings, future technologists to move into the field, and if nothing else, continue to stimulate the discussion. And it's all incumbent to us to actually help improve the health of our fellow human beings. So with that, I'm happy to sign off. Thanks also to the co-organizers of the conference, And I'm looking forward to meeting all of you in person sometime soon. Thank you.
Thank you.
Thank you all. Bye.